I touch the button. Ok, no problema. Entonces, now y is equal r sine theta. Ajá, es the equation que is used to conversion from polar to Cartesian, no? Oh, okay. Another possibility is r squared is equal x squared plus y squared, and also theta is tangent inverse of y over x. So this is a set of the equation that allow us convert from rectangular or Cartesian to polar, and this is the set of the equation that we convert from polar to Cartesian. Right? So now, okay, what is the idea? The idea is you take the function, you replace no x anymore, you put r cosine theta, comma, r sine theta. If you algebraically, when you are doing that substitution, you can separate. No, not always possible, but sometimes it's possible. So you separate variable. So I suppose that I have capital F, que depending only of the R, and multiplication capital G, que depending only of the theta. When you apply the limit, for example, suppose que es 0, or 0 plus, because, you know, it's always that distant, no? R is that distant, no? To say approach it to 0 of this. Multiplication, limited, when the R approaches to 0 plus, because 0 plus because it's positive, no? It's distant, G of theta. Entonces we can compute that limit. And frequently, well, no, okay, this is one number, any number. But this do not depending of R. So this is, and also is bounded. It is bounded. So give me a number. You compute the limit. Bam. L. Right? It's a one fantastic strategy. How do you know? I don't know. You try. So it doesn't work, so we have another technique. But I bring, I suppose, 3 examples. Example 1. Okay, compute the limit when the x comma y approach to 0, 0. The majority of the example is 0, 0, but not necessarily 0, 0. This is a casualty. It's a coincidence. Suppose this limit. Okay. Okay, so I make a decision. Wow, I want to convert to polar coordinate. Okay, so apply the limit. In that case, r approaching to 0 plus. Okay, so you replace. This is r cubic cosine cubic theta plus r cubic sine cubic theta divided by r x squared plus y squared is r squared. I know that, r squared. Now you see clear que you can factorization r cubic. So we have cosine cubic theta plus sine cubic theta. I have no idea who is that, but I don't care. Divided by r squared. It's obvious that you cancel out simplification here. Stay one r here and cancel out here. And you separate into limited. The first limit is limited, and the r approaching to 0 plus. Of the r alone, one r stay alive. Multiplication, another limited. R approaching to 0 plus. Of the one part that do not depending of r. Is and by the way, it's bounded. Because I know very well that sine is oscillating, sine and cosine both are oscillating function, vary between -1 and +1. So this is not important. This is not important. This is just Nothing. Now this is 0. It's obvious, plugging in 0 here is 0, and the answer of the limit is 0. Done. End of story. Do you understand? Do you understand or no? Cool. Cool. It's equal to 0. Yeah, it exists. It's equal to 0 and exists. Another approach is very, very, useless, because you never get the conclusion. You need to prove in different way. Apply one easy change of variable. I changed my problem from rectangular Cartesian to polar. You see different point of view. Different, totally different point of view. Let me see example 2. A little bit more complicated, but no big deal. Suppose the limit when the x comma y point approaches to the origin again. Entonces we have parenthesis x squared plus y squared. And we have here natural logarithm of x squared plus y squared. This is the function que is inside the argument of the limit operator. Entonces immediately I do the transformation to polar. Okay, entonces I change the variable. Entonces now it's limited. By the way, another advantage is you convert the problem multi-variable, and one problem is single variable, like a calculus 1, 0 plus of the r square multiplication by natural logarithm of r squared. Okay, as always, guys, as always. Well, this is calculus 1. Look, it's classical idea. When you try to compute limit, you plug it in. So this is 0 squared gets 0, no? And natural logarithm 0 squared, 0 squared is 0, but natural logarithm 0 is infinity, negative infinity. So actually it's 0 times negative infinity, que is indeterminate. Entonces I need to do something. Bueno, in calculus 1, the idea is clear. In calculus 1, you, for example, you try to change the indeterminate from the classical 0 over 0 or infinity over infinity in order to apply L'Hopital rule. Let's do it. For example, I manipulate algebraically here. I take natural logarithm of r squared over 1 over r squared. I move this as a square in the bottom, like a reciprocal, no? I'm plugging in again. I omit the word limit, no? Because I want to focus in that part. Entonces now again, one more time, we have minus infinity. When you plugging in r. Okay, well, so you want to write again. Limited when the r approaches to 0 plus over infinity. Because 1 over 0 is infinity. Okay, ready to apply L'Hopital, L'Hopital. And L'Hopital, you know, it's easy. Yes, you, for example, differentiate the top part. Derivative natural logarithm is, bueno, chain rule, guys, chain rule is 1 over r squared multiplication by derivative argument, que es 2r. Cool. And derivative this, this is r to the minus 2, no? Derivative this is minus 2 r to the minus 3, no? But I don't like negative exponent. I want to put directly r cubic, right? Okay, cool. So let me focus it in the top, guys. I hit copy again, limit word. I focus in this expression algebra. I manipulate a little bit. This is 2 over r, no? Because this r is cancelled out with the 1 here, and we have here minus 2 r cubic, no? Actually is 2 over r times r cubic divided by negative 2. No, this is negative r squared, right? Beautiful. Now I copy, limit it when r approaches to 0 plus of the minus r squared. And plug it in and see when you plug it in again, we have indeterminate. We need to apply several times L'Hopital rule, but in this case, no, because when you plug in a 0, actually 0 is 0, 0 have no sign, so don't make sense to say negative 0, it's 0. It is. Everyone follow me? Easy or complicated? Easy, right? Opinion, guys, opinion. Do you follow me? Totally lost? One part I don't understand?
Easy.
Easy, okay, super. Follow, okay, good. Now, I bring another example of the polar transformation. Entonces, polar is the key que open the door anytime? No. This is one strategy. And sometimes applying this example que I bring, but in another example, no. And another example working, for example, another strategy that I want to explain today, no? Pero, okay, suppose this limited, okay, and this is x squared, y squared, over x squared plus y squared. Polar. It's similar. I suppose that this example do not apport too much information. It's the same thing. This is r squared cosine squared theta. This is again r squared sine squared theta divided by r squared. Entonces r squared cancel. You separate limited when the r approaches to 0 plus of the r squared. Here we have another limited, no? That is limited when the r approaches to 0 plus of the cosine squared theta and sine squared theta. This is not important. It's just a number, but this is 0. The answer is 0. Okay, you see, wow, but any problem, the answer is 0. No. Not necessarily. This case is a coincidence. Suppose example 4, and this is the last one about polar. Okay, it's limited when the x comma y approaches to 0, 0 of sine x squared plus y squared divided by x squared plus y squared. Wow, this is easy. Because one more time you see this is equal limited when the r approaches to 0 plus of the sine r divided by r, r squared, sorry, divided by r squared. Then you change the variable to the polar, you convert the problem the multivariable and single variable, calculus 1. And you know very well that the limit, calculus 1, you know the fundamental trigonometric limit, x approaches to 0 of, no, x approaches to 0. Something approaching to 0 of sine something divided by something is equal 1. You remember this in Cal 1, right? Fundamental trigonometric limits. So this is 1. End of story. End of story. This is 1. Cool. Now you take advantage. When you see x squared plus y squared, and you see several power of this, entonces es obvio que polar worked. And that's it. No. I bring another strategy que es super strong. Que es squeezy. There. Squeezy. Squeezy theorem. Okay, Squeezy theorem. Squeezy theorem, in my opinion, is like a magic. Because what is the idea behind? Let me refresh your memory, Squeezy theorem. Suppose that we have three functions. One function h, one function f, and one function g. And you prove mathematically, no super complicated part, that f is in between that function. So one geometric interpretation of this idea is, suppose they want to find the limit in one specific point here, x, single variable, calculus 1. But f is very, very complicated, very, very hard to evaluate. Because f is something weird. Algebraically it's complicated. However, we discovered that we have one h that is not complicated, and we have another g that is not complicated. But the idea, the important idea is, in the famous point A, I want to approach it. This behavior satisfies this inequality. Entonces, the Squeezy theorem say, wow, well. Entonces, you should do, in order to complicate your life, try to compute algebraically this limit. Too hard. Now we are doing the limit of both function in between, que es h and g. And see, by coincidence, this number is the same, therefore this number is the same. Boom. Okay, this is the idea. I suppose you remember, yes or no? So we apply this idea again in multivariable. Look at this example. Let me start from an easy example. Example 1 is the Squeezy limit when the x comma y approach to 0, 0 of the x to the 4th power divided by x squared plus y squared. And this example, you say, well, professor, I can do in Polar. Yes, you can. And you get the same answer. This is the beauty of the mathematics, right? However, in this case, I want to explain no in that way. I want to explain using Squeezy. And Squeezy is, look, you understand que es obvio que the expression x squared divided by x squared plus y squared for any value is in between 0 and 1. Because it's a fraction, you know, this fraction, our denominator always is bigger than, because it's in between this. If you multiply this inequality, if you multiply. Yeah. You see, David, no? You see, no, but you forgot, professor, que this is 4 and this is 2. You copy 2 here. No, entonces I am not sure que 4 satisfy this, but I am sure mathematically que something divided by something plus another quantity is in between 0 and 1. I am 100% sure. Now, you multiplication time by x to the 2nd power, this inequality. And when you multiply the entire inequality to the 2nd power, we get 0 less than or equal x to the 4th power divided by x squared plus y squared is 1 times x to the 2nd power is x to the 2nd power. Okay, entonces, suppose that limit is too hard. Bueno, no es too hard, pero bueno, no. because we learned before the polar, no? In polar, maybe we can do that. However, here, this is too hard. However, this is too easy. So instead of compute that limit, no. I compute the limit when the expression is 0. Okay, I don't know what put here, say x or y, doesn't matter. The answer is 0 because limit constant is a constant, no? And this case is x squared, and you take only one variable, no? It's 0 squared, okay, 0. See, both limits are 0 to say, I guarantee you that the limit is 0. Do you see that? Squeezy. Squeezy sometimes, guys, is a little bit sophisticated to understand this. Let me try one more example. Two more. One a little bit more complicated. So the sophisticated part is create the inequality. Pero es, bueno, es using a little bit imagination, ¿no? Common sense, imagination. Suppose example 2 now. Example 2 is a little bit more interesting. Look, suppose limited when the x comma y approaching to 0, 0. You see, one of professor always says 0, 0, the complicated point. No, next example is not 0, 0, it's another. X to the 6th power plus x squared, y4 divided by x squared plus y squared. Entonces, one more time, one more time, no. First of all, I saw, okay, we can, let me try to copy, no, the limit, the word, limit. I copy separately here, this expression. And why not? I factor out in the top x squared. Stay x to the 4th power plus x squared, no? No, y squared, sorry. Y squared. Y to the 4th power, sorry. Divided by x squared plus y squared. Okay. So in this moment, I realize, wow, this is similar to the other thing. I take this part. Ooh. I copy here separately. I know the x squared over x squared plus y squared. It's all because it's a fraction and between 0 and 1. And now we know you multiplication, this time x to the 4th power, this time plus y to the 4th power. Okay, by the way, this expression, this new expression is positive because it's raised to the even exponent. So now we get, well, this expression times 0 is 0. This expression times this is exactly the same, the original expression. Look at that. Look at that, this one. And the other side is just x to the 4th power plus y to the 4th power. And this is my famous function original que I discovered algebraically, que es bounded between 0 and 1 expression. And the limit is 0 is 0, pero the limit of this, when x comma y approaches to 0, 0, obviously is 0. Therefore, the is limit of the more complicated expression is always 0 by squeezy theorem. This is the justification. Cool. This is not a problem, you know, you solving in 5 seconds. No. You meditate, you try to elaborate your strategy. You follow me, guy, or no? Okay. One more. one more of the squeezy. A little bit more sophisticated. Example 3, no? S3. S3 was S3. Suppose this limit. Limited when the x comma y approach 2 comma negative 3. Wow, it's no 0, 0. Okay. Of the expression gets 2 x minus 2 squared divided by square root. Wow, what the hell? X minus 2 squared plus y plus 3 squared. Remember, the first thing you should do in any problem with the limit is plugging in. It's obvious that the answer is 0 over 0, no? 0 over 0. Okay, it's indeterminate. Does mean that we need to do something, no? So to simplification. Okay, so now I propose one idea. I take this expression, que es 2 parentheses x minus 2 squared divided by square root x minus 2 squared plus y plus 3 squared. And this is a fraction, no? And this fraction, bueno, es positive, it's obvious, it's positive because you suppose any expression square is positive, and the square root you take the positive part, and no plus or minus, the plus part. It's positive. But if you, for example, ignore that part, well, we have 2 x minus 2 squared divided by square root x minus 2 squared. Entonces now we have fraction. I delete mentally the y part because my intention is convert the problem of the multivariable calculus x and y and single variables now. And also when you remove something in the denominator, our new expression is greater than the original, no? Because when the denominator, you delete something, denominator decreasing, no? You see denominator decreasing, the fraction, the whole fraction increasing, no? So this is clear. Okay, it's no violation, it's licit, less than or equal, right? Because this expression is bigger than this expression, no? And this expression, wow, is 2 times, and this is square root and square cancel out, stay alive, x minus 2 1 time, and simplification is x minus 2. Make sense? Make sense? Do you understand this or no? Maybe you see, well, professor, I never see that, but when you need to train your brain, yes, Helene Perez. Now ready to apply a squeezy theorem. The squeezy theorem, one more time, I repeat, when you have a complicated expression, and you will be able to bound it in between one function, that this function is a constant, and another function that is not constant, but it's relatively easy. The only thing you should do is apply the limit in both points. Well, it's 0 here, it's obvious it's 0 here, because it's a limit, you convert this complicated problem in one easy case, x approaching to 2. 2 over x minus 2. So the y disappear because I delete here mentally, remember? And this is 0. Our limit is no indeterminate, is equal to 0 by squeezy theorem. Cool. I like this. I know it's sophisticated, it's complicated, but I like that. And this is the only strategy, polar and squeezy. No, we have another powerful strategy is rationalization. So when you see in one limit, this is classical, like a calculus 1. It's classical. Suppose this example. Okay, you have limited when the x comma y approach to 2 comma 1 of this expression can look like complicated, but actually it's not. divided by no, es minus. Sorry. Es minus here. Okay. Entonces you plug it in, as always, you plug it in, you don't know anything. 2 minus 1. Let me see, minus 1, yeah. 2 minus 1, 0. And here is 2 minus 1 is 1, square root 1 is 1, 1 minus 1 is 0. Indeterminate. Okay, so I copy the expression here. And you rationalize. Exactly the same way I do in algebra. Rationalization is do something in order to eliminate the radical. So you multiply using a smart one, square root x minus y plus 1 is a conjugate of this, and square root x minus y plus 1. Cool. This is artificially smart one. You know, any expression divided by itself is 1, but this one is smart because help me to simplification our problem. And now you multiply why not this and this. Okay, to make easy to understand, this is the binomial, and this is another binomial. But conjugate, right? When you do a multiplication of the conjugate, the answer is a squared minus b squared. Is a famous formula que everyone knows. Entonces, square the first, que a es considered like a radical, es x minus y minus b is 1, 1. In the top, we have x minus y minus 1 multiplication by square root x minus y plus 1. It's obvious that this factor and this factor cancel out. Now we discover que that limit is equal to that limit. Now I copy this expression, square root x minus y plus 1, no? I'm plugging it. Plugging is square root 2 minus 1 plus 1. Plus 1, no? Okay, I do it right. Entonces 2 minus 1 is 1, square root 1 is 1, 1 plus 1 is 2. Boom, finals. This is not new. You see before. In Cal 1, maybe, the professor explaining, I suppose, this idea, no? So the problem in which you rationalize, no? This is a classical strategy for solving the limit that gets repeated again in multiple. So far, it's okay, guys? So far, it's okay? Okay, so let's change. Yes, okay. Let's change now the topic. Let's do continuity. Continuity is similar. Continuity. It's similar to Calwa, but apply a multivariable. Let me refresh your memory, Calwa. Continuity, we need number one. Well, the definition is clear. It's the limit when the x approaches to a of the one function in single variable is equal the function. Evaluate this. So this equation involves three concepts. Concept number one, this limit exists. Concept number two, the function exists. And concept number three, both are equal. Okay? Similar idea in multivariable. Let's see example. So understand more clear. Suppose piecewise function. Example 1 continuity. Okay, suppose piecewise function is given in the problem, que es cosine y multiplication sine x divided by x. But this condition is valid for any other pair that is not the origin. No, origin no. And cosine y only if x comma y is exactly in the origin. This is a piecewise function, and you prove somehow que es continuous function or no, or discontinuous, que is another possibility. Okay, so now remember step 1, determine the function, evaluate at the point 0, 0, que es the point critical, no? So the only point que create conflict is supposed que es 0, 0. And x is in the denominator, division by 0. But of course you select in the piecewise function, you select this piece, because we are exactly on 0, 0. And you evaluate x cosine 0, que es 1. In this case, the piece contains only y, no x. Entonces you plug it in, this is x. But my function have no y, no x. I plug in y equals 0 here. And the answer is 1. Okay, cool. Now apply the limit, second. And prove that this limit exists. Si the limit do not exist, well, entonces now it's discontinuous. It's jump discontinuous. Of course, and the limit is not exactly in 0, 0. It's approaching in any direction to 0, 0. Therefore, we're using the second function. Que es valid for different value, not exactly 0, 0. Entonces you take cosine y sine x divided by x. And you plug it in. Wow. Entonces you will plug in cosine es 1, pero sine es 0. Uy. And this is 0. 0 over 0. Entonces, again, one more time, it's indeterminate. I need to do something in order to find this. But this is super easy. I select one example easy. Suppose you separate this similar idea for the polar. This function is separable. So you for example, you separate cosine y alone, multiplication by limited sine x divided by x, no? And this is y approaching to 0, and this is x approaching to 0. Wow, fantastic. I like that way. And you plug it in. This is 1, cosine 0 is 1, and this is the fundamental trigonometric limit, que es also 1. Entonces the answer is 1, and this 1 is equal to that 1. Now the function, it is continuous. It is continuous. Continue at R2. So the entire space in 2 dimensions is the domain. Huh? In this case, because this function, the domain is 2D, and the function, the graph is in 3D. Cool? Do you see this example? Straightforward, elementary. I select sophisticated example. But the majority of the scenario, for example, you have nice function, like a polynomial function. For example, rational function, but inside its domain, exponential, sine and cosine, no tangent, no secant, que are continuous. Entonces, the combination of this function is obvious que es continuous, and you don't need to prove anything, because you see, well, okay. Suppose, hypothetically, suppose f of x, comma y is equal sine, paréntesis, x squared cosine y. What do you think? To do anything. It's continuous or no? Oh, yes, because the composition, cosine, sine, power, everything is continuous. Entonces, the conclusion is continuous. End the story, and the limit always exists, and the function always exists. Maybe we have domain and range, but this is not the point. The point is continue, to be continued. Okay, let's do another problem that look like complicated, a little bit different. Let me try to continuity, example 2. Example 2, continuity. Okay, there you go. Look, suppose the piecewise function again. Okay, it's the complicated guys, ¿no? Because the function is in one piece. Entonces es obvio, ¿no? Es more clear. Pero si es piecewise function, bueno, sometimes we have critical value in the connection, ¿no? And the pieces. In this case, again, is the S in the origin. The function is 0 in the origin. And the function is y4 divided by x squared plus y squared if x comma y is no origin. It's in another point arbitrary. And I want to proceed continue or no. I suppose it's continue in any point, but in 0 no. In 0 is the point that you need to focus. I need to pay attention in 0. And number 1, evaluate in 0. Evaluate f en 0,0, que es obvio, que es 0. This 0 is this 0. Right? And now second, I apply the limit. Limit when the x, y approaches to 0,0 of this expression. Okay. Entonces I want to apply maybe, I am doing my paper bipolar, but you can use squeezy. Squeezy is sophisticated. Squeezy is a little bit sophisticated. Okay, squeezy is more sophisticated because you need to create the inequality, you know, and there's sometimes you don't see clear. So now, okay, I decide, polar. Why not? So now, substitution, this is R4, sine, sorry, because it's y, sine, 4 power theta, divided by R square, no? Oh, this is R square. Use simplification, entonces R square, sine 4 power theta. Now you apply the limit. Oh, yeah, I convert using my common sense and my imagination. This limit is multivariable, and one limit is non-multivariable, 0 plus of the R square. And sine this is bounded, it's not participating in the game. Limit the R approaching to 0 of sine 4 power theta. This is bounded, and you apply here is 0. Is 0, that 0 is equal to 0. Conclusion, it is continuous also in the completely plane R square. Cool. Okay, entonces, what is the reason, professor, que we study the limit? Bueno, we study the limit because I want to introduce en calculus, ¿no? Y en cálculo, for example, the derivative, o sea, we study now derivative in multivariable, ¿no? Entonces, the derivative in multivariable, let me recall Cal 1. In Cal 1, the formula to find the definition to find the derivative is limited. Well, at least one definition. There are two definitions, but the most popular is this. Cool. Entonces it's a little bit complicated to understand. Okay, look, to one function is differentiable in Cal 1. In Cal 3 is different, but in Cal 1, the first condition is to be continuous. If we have discontinuous, at the point gets discontinuous, maybe jump discontinuous or removable discontinuous. Either way, is not differentiable. So one condition to be differentiable is to be continuous, but not enough. Because sometimes we have sharper point here, right? And this is continuous, but not differentiable. So in order to find, I need to find this limit. And this limit, see, this limit do not exist. It's not differentiable, right? And we take advantage. We take advantage this definition. Entonces en Cal 3 we define one new thing que es called partial derivative. Partial derivative. Pay attention. Partial derivative is not the total derivative. It's one piece that we need to study to understand the total differentiation. Entonces, what is that? Bueno, es derivative, pero in one direction. Remember, we have infinity possibility. We have a point, we have infinity possibility of the direction. You differentiate in any direction. In Cal 1, you differentiate only in one direction. In Cal 3, we can differentiate in any direction. Okay, pero entonces I need to make something, well, at least professor differentiate in the direction X, similar to the Cal 1, y in the direction Y, que es the standard direction que you frequently work. And this is the final answer. This is total differentiation. No, this is partial. This is the idea that this is the idea why this name contains first name, derivative, and last name, partial. Because it's not total. Entonces, bueno, okay, too much, blah, blah, blah. What is the definition? Definition partial derivative. So we need to be familiar with the notation first. Notation. There are several notations, and you need to be familiar with any notation. And you see what is the most popular and what is not most popular. Suppose the function, and when you differentiate with respect to the x direction, you put the subscript here, x. This is one possibility. I like this notation. I like also that notation. df dx is another notation. So this letter is Greek letter delta. You see, Professor, delta is so in physics is this. But delta is a capital delta, capital letter, and this is lower case letter, delta. It's delta. And this is, remember, the classical controversy between Newton and Leibniz. Newton and Cal 1 say F prime, and Leibniz say dy dx. Right? This is Leibniz, Germany, and this is Newton, British. Right? Entonces, this is, we have two notation, no? Historically. However, we have here two notation. Newton notation in partial derivative and Leibniz notation in partial derivative. Okay? Entonces dice, wow. Pero what's the reason que es delta or not dy dx? Because this indicate ordinary derivative. Ordinary derivative is when in the chain rule, y dependent of the x. But in this case, no. It's partial because maybe z depending the x or depending the y. Then we have two different paths, and to indicate this, you using delta because it's partial derivative. It's important. You need to be aware that sometimes in calculus we have ordinary derivative and we have partial derivative. Okay, another notation that frequently never using is capital DXF. Likewise, partial derivative with respect to y. df dy or dyf. And we have first derivative, but we have second derivative and so on, higher order derivative, no? And suppose the second derivative with respect to x to time is fxx. Second derivative with respect to y is fyy. And in the Leibniz notation is second derivative f with respect to x. And this is second derivative f with respect to y. And we have a combination. Why not? We have Derivative first with respect to x and derivative second with respect to y. Entonces, the notation is dx first and dy second, ¿no? In this direction, yx is second derivative f, and you derive first. In this case, you derive y first and x second. Cool? Pero this is the notation, pero I suppose que I skip the most important moment, is definition. What is the definition? What is the definition? It's exactly the same definition of this. This definition in Cal 1 and partial derivative is exactly the same definition, but in only one direction. So what is the partial derivative of x, for example? Bueno, es el limit when the h approaches to 0 of the quotient rule, ¿no? Que es f x plus h. Look, sometimes it's similar, comma y minus f of x, comma y divided by h. So you suppose que the rate of change que I want to investigate is only in the x part, and the y stay constant. This is the idea. The y stay constant. We travel. I promise que in a few seconds you see the one script I created for you and algebra. You see the geometric interpretation of this. And likewise, is the limit when the h approaches to 0 of the f x comma y plus h. I don't know, I'm using the same letter with some books using h and k, but it's not important. Cool. Definition. This is definition. This is definition. Entonces, what is the manipulation algebraically? Que is the most important part. Well, not the most important, but it's super important. Let me try to understand this. Suppose example 1 to understand partial derivative. Algebraic manipulation. Wow. Look, you have function. Not complicated, polynomial. The QB minus 2y squared. I want to compute partial derivative f with respect to x. Pay attention now, please. You consider in the partial derivative with respect to x, you consider that the y is constant, no change in the direction of y. Therefore, when you differentiate, you consider that y cubed and y squared is just a number, no variable. The only variable that we have is x. The derivative is power rule, is 3x squared, no problema. This is clear, everyone understands very well. Now you differentiate that part as 2x and y cubed stay the same because you consider it like a multiplier. Okay, it's a constant multiplier, like a 20, like a 4. And this no, because it's a constant, but constant no multipliers, constant outside the game. Now derivative of the constant is 0. Cool? Likewise, partial derivative with respect to y. Derivative is is 0 because do not depending on y, and derivative is 3x squared y squared. And derivative is minus 4y. Let me check it. Yeah. Do you follow me? Do you follow me? Do you follow me? Do you follow me? Okay. No. I promise we are doing more example. But now I want to continue with the theoretical part. So now interpretation first derivative, partial derivative, sorry. Interpretation, geometric interpretation of the partial derivatives. I try to open here one script of the Algebraic I created for you at this moment. Okay, partial derivative. There you go. Okay, let me share screen. Share screen. Algebra, partial derivative. Boom. Boom. Do you see algebra? Do you see? Yes. Okay. Well, I create paraboloid. Look at that. I create paraboloid. Entonces, in this paraboloid, I put the specific point A, I put in red color. Okay, I can handle here the position of this. So I move X component, Y component, a specific point. Now, understand partial derivative. Suppose que I suppose que I differentiate with respect to Y. Derivative, first derivative, partial derivative with respect to the Y. So I consider que X es constant. X is constant, the representation is a plane. Look at that. X equal something is a plane perpendicular to the x-axis. Remember, x-axis is the red one. Entonces, this is x equal constant. I can change. Look, I can change. X equal constant. And the intersection between the paraboloid and the plane is a parabola. It's obvious, no? But this is not important. It's the parabola que I put in black color. Okay, now you want to see more clear. I want to delete the plane. I want to delete the paraboloid. I see the parabola in the space. I see the famous point. And the tangent line, see the tangent line at the point A, I put here. No, it's that one. That one. And when you move, no, not this. When you move this, you see, get the same idea of the calculus 1. Is this. So the derivative represents the slope of the tangent line, but in this case, in the direction, okay, you, in this direction is the y direction, no? Because I assume the plane x equal a constant, okay? X equal a constant, and here you have cal 1, pero in the y direction. Yes or no? Do you see or no? Do you see or no? Do you see or no? Yes. And the other is similar. Likewise, let me try to do my best. We come back, so no line anymore, no parabola anymore, paraboloid again. That's it. And the plane is y equal constant. Bam. It's a plane perpendicular, no, to the green axis, que es the y-axis. I can change if you want. Look, change. And the intersection in between this guy is the another parabola, no? Because it's paraboloid, no? Paraboloid. Paraboloid generate or parabola or circle, no? Or ellipse, maybe, when you are doing z equal constant. And the line, the famous line, I suppose it's this. I don't know if it's this or this. Let me see, I am confused. It's this one. Let me see. Oh, yes, it's this one. To see more clear, you delete that. And you see the parabola again. You see this tangent line. And the specific point. Cool. It's the geometric interpretation. It's the same thing we studied in Cal 1, but apply in multivariable. The only thing is that you need to understand is the partial derivative not necessarily is the full derivative. No, it's not differentiable in the whole direction, in any direction. It's in one specific direction. That is a reason it's called a partial in the story. Any question? Any question? No question. Cool. Okay. Just let's practice a little bit. A little bit, not too much. The rest you need to do by yourself in the homework. Okay, by the way, I need to check in the due date. Switching to whiteboard. Do you see whiteboard? Do you see whiteboard? Okay, let's do it. Let's do it. Let's do it a couple of the example. A couple. Okay, easy, not complicated. Because it's cal 1. Suppose the function is equal x squared y squared. Easy, piece, okay. But I need to compute a lot of things. We need to compute partial derivative with respect to x, partial derivative with respect to y, second derivative, xx, second derivative yy, second derivative xy, and second derivative yx. Cool. So, I need participation. Come on. You consider, remember the partial derivative, you consider, suppose que you differentiate with respect to x, you consider que y is constant. That's what the answer. Help me, guys. It's easy. Uh, 2xy squared. Cool. 2xy squared. And what about partial derivative with respect to y, in which you consider que x is a constant? 2yx squared. 2y, this is Davy. Davy is the best. X squared. Or 2x squared y. Putting alphabetic order. This doesn't matter. It's not important. This is cosmetic part. But I like the beauty in the mathematics. X squared y, no? Okay, cool. Now differentiate 2 times. So you don't need to do again 2 times. You take this expression now, this one, and one more time you differentiate with respect to the x. Second derivative, 2 times xx. You are doing 1 time, and you are doing 2 times. And you are doing 2 times. Differentiate with respect to x. Come on, help me. Come on, guy. Oh, participation, not only Davey. Davey again. 2y squared. Cool. So you don't want to type in, you activate the microphone and you say your answer. Okay? I don't want to ask your name. No. 2y squared. Everyone is agree? 2y squared. And y. You take this and differentiate with respect to y again 2 times. Is 2x squared. Beautiful. And xy. So what? I differentiate first with respect to x. I did that here. And differentiate with respect to y, please. Differentiate is 4xy. Super cool. And now you differentiate with respect to y first. I did that here. And differentiate this guy's expression with respect to x. It's 4yx or xy again. So you put in alphabetic order. Notice, it's no coincidence. It's a fact. Always the partial derivative is totally independent of the order. You are doing differentiation in different order. This is theorem. It's a fact. Okay? Cool.
Professor.
What
is the last thing, f with sub x sub y?
Okay.
It's partial derivative of y and x. It's not the full derivative.
Okay. This is fy. I did that. Okay, was 2x squared y, correct? I want to differentiate this with respect to x now. So you consider that the only variable that we have is this. And the derivative is these 2 fly in the front, and 2 times 2 is 4. And you decreasing 1 here, x and y stay the same because y is considered like a constant, like a one number. This y, the behavior of this y is exactly the same behavior of these two. Okay, and you consider like a multiplier. More clear now? More clear now? No?
I still don't understand what you're taking the derivative of.
Well, but you don't understand.
Well, are you like differentiating both x and y?
You say this example. You don't understand this example.
No, I get the first partial derivative of x and the first partial derivative of y and the second partial derivative of x and y. I don't get the last two parts. The f x y and that.
Let's do it again. Let's do it again. Let's do it again. I try to do one more time. Focus. Look, I need to differentiate with respect to x. I did that. The answer was 2xy squared. And you now differentiate this expression with respect to y. So you focus in the y variable, and the rest is no variable. It's a constant. The 2x go outside the game, and the derivative this is 2y, and 2 times 2 is 4xy. Cool? Cool?
So it's the partial derivative of y?
Okay, this notation indicate xy is you differentiate first with respect to x.
And then y.
Exactly. And after.
Oh, okay.
Two operations. Okay. Two operations.
But you have to do x first? Or
absolutely,
x
absolutely. I did in different way. Look. I did that. This is partial derivative with respect to y. I did that. The answer was 2x squared y. I suppose you understand this. You say you understand this. Now you differentiate with respect to x this new expression. Therefore, the only variable we have in the game is x, because you differentiate with respect. And the rest stays the same outside like a constant. And you differentiate x squared is 2x. And multiplication for xy in alphabetical. By coincidence, no, it's a fact. This derivative is the same. Also, yes or no, mister?
Perfect.
Excellent. Do you want one more example? I try to find. No, sure? Sure?
Yeah.
Yeah, well, I mean, yeah. More, yes, more example, no?
Definitely sure.
Okay. Your answer, yeah, okay, it's not clear for me. You say more and more. More example, no? One more example. Okay. No big deal. No, because it's Cal 1. It's just Cal 1. Suppose this example. Fx comma y equal x squared plus 3xy plus 2y squared. I want to compute everything. Differentiate with respect to x first, differentiate with respect to y second, differentiate xx 2 times, differentiate yy, differentiate xy, and differentiate yx. This is the order in which you differentiate. So first of all, you differentiate with respect to x. You consider that x is the only variable that exists in the world, and the rest is constant. It's just a number. Cool? Who help me? Come on. Come on, guys. I need to explain one more thing. This is Cal 1. 2x plus 3y. Super cool. 2x plus 3y. Another participation. And now you differentiate with respect to y. This is 0. This is 3x plus 4y. Cool. 3x plus 4y. Everyone is agree or disagree with this differentiation? Cool, agree, Ernest. Second derivative with respect to x 2 times is Helen is good. I suppose que Helen is like this. Understand, no? When you understand something, you say it's good. Entonces, the second derivative, xx, what is that? Guys, this is important. You need to master. That's too cool because you differentiate this expression with respect to x. Cool. And y. So you differentiate is 4. Cool. F4. F4. Now fxy. S3 is a number, okay, okay. And fyx, I suppose que it's the same value, no? Is S3. Always happen que this guy is equal. Always. Do you understand much better now? Do you understand much better now? Huh? Yeah? Okay, let me explain the rest of the time to introduce new idea. The chain rule, the famous chain rule that we study in Cal 1. We study a multivariable calculus, but it's a little bit more complicated because in Cal 1, basically you have y dependent x. That's it. So the change contains only one step. Only one step in the change. However, not always happen in this. Suppose, let me try one example. No? Suppose this example is the function example to explain the chain rule is example. Suppose z is equal x squared y plus 3xy4. But x depending of two new variables is sine 2t. And y depending of the another variable is cosine t. So now the tree can represent the chain rule is a little bit more complicated. Is c depending of x and y, but x depending of t and y depending of t. This is important to generate this tree because this tree give me the expression or the formula, specific formula for the chain rule in any problem. So let me try. Suppose I need to compute the ZDT. Wow, Professor, what is the reason you put ordinary? Ordinary, because it's the total derivative z with respect to t in any direction. So you travel, for example, for this direction and this direction, and this direction is partial c with respect x time dx dt. It's important to understand that this derivative is partial because c depending x and y. However, this derivative, no, it's ordinary because it's the Cal 1. It's x dependent of the t. Guy, this is this example. Another example is different. Maybe it's partial, everything. But I am focusing on one example. No? Now I finish. No, I have another trajectory, this and this. This is plus partial z with respect to y times dy dt. Important, repeat again, this derivative is ordinary. Cal 1. This derivative, no, is partial. Cal 3. Good? It's doing. I am using this notation now. Frequently, in the in the paper, I use in different notation, no? Because I need to adaptate you in different notation. So let's compute it separately, one by one. dz, delta, c dx. Now you differentiate this expression with respect to x. Es obvio que es 2xy plus 3y4, correct? And this guy is this in the formula. Now the z dy. Okay, again, I come back to the relationship, but yeah, differentiate with respect to y. You consider that x squared is a constant, stay the same. Derivative dy with respect to y is 1 plus 12. Where come from 12? 4 times 3 x y cubed, you know? Cool. I did that part. And you differentiate separately, like column 1, dx dt, que es derivative sine cosine 2t, and derivative argument is 2, remember the chain rule, and dy dt is derivative cosine and minus sine. Okay, now I put everything together. What is my final answer? The ZDT. Okay, I come back. It's this. But okay. Definitely, this is multivariable calculus. We have one independent variable, but we have two intermediate variables, x and y. So now, if you put together, mix it, t, x, and y, crazy. No, it's not good. Frequently, you put 2 times x, but who is x? This is x, sine 2t. Y, who is y? Cosine t. Plus 3 times y, que es cosine 4 t. And now multiplication this by dx dt, que es 2 times cosine 2t. The thing I don't want to do is a multiplication, combine like term, but basically this is the idea, no? Plus, I did that part, or I try to do my best. Now, and the last part is, is x squared, but x squared is this guy squared. I mean, this guy squared que es this, no? Es sine square to t, okay, plus 12 sine to t cosine cubic t, que es y. Multiply everything by dy dt, que es minus sine. Okay, I suppose que this is negative. And the algebra elementary, I don't want to do this. I suppose you know, you understand very well. Cool. Cool. But this is the most elementary chain rule that we can find in our life. We have another more complicated tree. Okay, we'll display now. Why not? Example 2, chain rule. Chain rule is multivariable. Example 2. Suppose que I have a function. Suppose C is equal e to the x sine y. And who is x? No, x is s times t squared. Wow. In that case, we have two independent variables. y is equal z square, s square times t. Okay, I want to compute partial z with respect t. And why no with respect the and partial z with respect the s. Oh, professor, I don't understand something. And the first example you put ordinary. Oh, the reason is because we have only one independent variable, like in column 1. We have two intermediate variable x and y, but we have only one independent variable. In this case, no, we have more degree of freedom. We have two independent variables, que es s and c. That is the reason que es have no sense to talk about ordinary derivative c with respect to t. No, because we have two independent variables. Okay? And the 3 is z dependent of x and y. You see clear in this expression. But x dependent of s and t, and y dependent of s and t. This is our 3. This is our 3. And the formula, que es derivative for that 3 is, suppose, partial derivative z with respect to x, you travel for any trajectory that involves somehow, sorry, I make a mistake here, is suppose t, right? We ending in the independent variable. Entonces, this trajectory is this, and this, and this, and this. Entonces es partial derivative z with respect to x times partial derivative x with respect to s plus partial derivative z with respect to y times partial derivative y with respect to t. This is the formula for the partial derivative z with respect to t. Okay, now partial derivative z with respect to s, similar, no? Es partial derivative z with respect to the x times partial derivative x. I make a mistake here, right? This is t, no? This is t. We travel for t path. Now we travel for the s path. Now it's partial derivative z with respect to y times partial derivative y with respect to t. Boom. Do you see that or no? And the rest is piece okay. My recommendation is do step by step, separately, and finally plugging into the formula, no? I know that the time is over, no, it's okay. However, next time, well, we finish, no? We finish this example. We almost finished.
Professor? At the very end, is that supposed to be dy or dy over ds? Or is it supposed to be over dt?
I mean, what's the question? dy over dx. Dy over dx.
At the very end, at the bottom, what you just wrote, the partial derivative of z over ds. Like, look all the way to the end of your line. You have delta y over delta t.
Okay,
what delta s?
I don't understand. What is your question about this equation?
No, the one below it.
One below. The one below this.
Yeah, is what you just circled right there. Is it supposed to be a ds at the bottom?
Yeah. Remember, we have two independent variables, s and t. I want to differentiate the original variable, dependent variable, like a function of the two independent variables, que es s. Entonces, what is your point? What is your question?
I was just seeing if that was a mistake at the end, if it was supposed to be an S or is that actually supposed to be a T?
Let me compare. This is the same. This is no. Replace T and S. This is the same. And this is, oh, yeah. So you say that one. Okay, it's S.
Yeah.
Super cool. Super cool. All right. Okay, guys, we finish. Just have a nice day. Bye-bye.
Bye, Professor.
Bye-bye.